Welcome to our wonderful world of Graph-Translation Theorem today. Sounds fancy schmancy, but you already know this one. This is all review from Algebra 1. So we're going to demonstrate vertical and horizontal shifting. That's what this word here means. Translation just simply means to shift. And please, when you write the word shift, make sure that the F there does not look like off kilter. Some people don't put their F's there, and then it kind of looks like a bad word. Wait. So don't do that. All right, especially if you're talking about shifting, and you don't have that little thing. Hashtag, that's happened to me before, my students. Okay, so let's compare the graphs here. How are we going to do that? Well, I'm going to pull out my handy-dandy graphing calculator, and I'm going to do that. Okay, so here I am, and I need to know what my functions are. So first off, I have y equals x cubed. Sorry, and that should be an x. And the next one is I need my y minus 25 is equal to x minus 12 all cubed. Okay, now how to analyze this. We are going to choose a point, and I said might as well choose the vertex right there. So this vertex is 0, 0. And notice where it goes to as we adjust our window here. Notice that the point up here, which is really hard to tell what it is, but it's about 12, 25. So if I were to plot that real quick, 12, 25. Notice that's going to be right there. So describe or compare the graphs. What would you say? What would you say about the shape of the graphs? They are exactly the same. The shapes are exactly the same. Is it wider or stretched out at all? No stretching. Is anything flipped upside down? Nope. So essentially all we've done is copied this one and pasted this one somewhere else. Okay? So, and if we see this point goes to that point, all it does is move up and right. So if we had to describe what was going on, we would say in this case, the graphs are identical shapes or congruent, and essentially all they've done is moved over. And we could even specifically see how much. We've moved up 12, sorry, not up 12, up 25, and right 12 there. So there we go. That would be our explanation there. So today we're going to be chatting, like we said, about the translation image of a graph. The first thing to talk about is the word transformation. Trans means to go across, like a transatlantic flight flies across the Atlantic. And of course, form, you know what form is? That's just your basic shape. So this means to change shape. Transformation, transformers. But here's the technical term. Here's the technical. It is a 1-to-1 correspondence. And I got a D there, correspondence of data. So there are 4 types of transformations. The first one we're going to look at is called a translation. Translation pretty much means to slide, okay, or shifting. A couple others that we're going to see. We have a scale which acts as a stretch or a compression, which we've seen some of that before. We also have something called a reflection. Flip it upside down or flip it to the left. And the last one is called a rotation. And an example of a rotation is this. There we go. Hashtag we got it all. So we're going to focus our attention on translation. Stretching and reflection are very closely related, so those are often brought together, and we're really not going to spend much time in rotation at all. Okay, so today we're going to focus on the first, which can simply be described as shifting. Some people like to say sliding, just sliding the book over across the desk. So in a transformation, one set, this is called the pre-image. There is no hyphen there, but that's how it's said. Pre-image is mapped to another set of data, and that's called the image. So in the image that I see in the mirror, I see an image, so I am the pre-image. I am the original object. So this here is the original object, the double OG. We've already talked about some shifting before, so let's just run through a little bit here, see what we get. Notice my first function, f of x, is just the square root of x. So really it's just 1, radical 2, radical 3, 2, radical 5. And so g of x would be what? Notice all I'm doing is adding 5 to whatever I got before. So this one's a 6, a radical 2 plus 5. This one's a radical 3 plus 5. This one's a 7. And this one's a radical 5 plus 5. So take a moment to either plot those points by hand or sketching it by using your graphing calculator, and then just sketch it out real quick. Go. So this one here is f of x, and when I plot that, it looks something like this. And notice what happens here. If I were to plot the other one, I'm beginning here at the 6. And, oh, did I mess up? That one's actually not at 0. Should be right there. Oh, no, that's right. 0, 0. It's the 1 that goes there. All right, so let me clean that one up. This one here starts out at the 5. Then it goes to the 6 there. And then etc. So what are we noticing here? The key thing to notice is each of these individual points is doing what? It's just moving up 5. It's just moving up 5. And what's nice is, as we are looking at my original function, I see that there is an up 5 correspondence there. An up 5 correspondence. So, in this context, I'm going to call this one the pre-image, the original. And I'm going to call this one the image. That happens the secondary situation. So this translation can be written in 2 different ways. So we can say capital T for translation of a point, xy, like a new function, is equal to x plus 5. So this sounds sort of funny, but this is the new function, based on the translation of the original points. They get changed to x does not change, but y does change. We add 5 to that. Another way to write it looks like this. The translation of x and y points gets sent to, or gets mapped to, x, comma, y plus 5. And this is how we read it. xy is mapped to x, y plus 5. So x doesn't change, but the y does. And we usually say is mapped to just talk about the shifting that occurs. So this brings us to the last thing we'll talk about today, the definition of a translation. A translation in a plane is the transformation that maps each point xy onto just a new, this one here is shifting to the horizontal, either up or down, or left or right. And this is going to be a vertical shift, up or down. And notice here that it says that h and k have to be constant. We're not going to be changing them as we go. So any changes to x shifts the whole thing left or right. Any change to k moves the whole thing up and down. So on page 2 here, we have a translation, and the image of. So please insert the of there. It's important that we have the image of. So in other words, this is my pre-image, 0, 0, and it gets translated to negative 12, 5. So find a rule for this translation. So remember, there are two ways to write the rule. We can write it like this, and with an equal sign, or we can say that t with a colon and have our point, use our fun arrow, and go somewhere else. Okay? So our original point here is 0, 0, and it simply gets mapped to negative 12, 5. Or I say the translation of 0, 0 is mapped to negative 12, 5. So two different ways to write that. Practically speaking, notice what we do. Starting at 0, so we go left 12, 0, right 5. Left 12 and right 5. So go ahead and talk real quick with your neighbor. What would the image of 6, negative 10 become using this rule? So let's unpack it a little bit. Wherever you start, all you have to do is effectively move left 12 and up 5. Okay. So that's right here. So if I were just to subtract underneath like that. So the 6 gets mapped to negative 6, and the negative 10 gets mapped to negative 5. So there is my second answer. Straight arithmetic on that. All right, our super secret theorem that we're going to talk about today is called the Graph-Translation Theorem. It sounds complicated, but really it means two things. So let me read it, and then we'll unpack it. So given a pre-image graph described by a sentence in x and y, so a sentence can be a function, or it can be, like this being a sentence, something like that. The following two processes yield the same image, replacing x by x minus h, and y by y minus k in the sentence, or applying the translation, xy is mapped to x plus h, y plus k, to the pre-image graph. So let's just unpack what each one of these mean. This one is essentially finding a new function from the equation. It doesn't have to be a function, a new relation, but we'll say function. This one here is about moving the graph. Moving the graph. Both of them are going to yield you the same image. So either I replace x with this and get a new function, replace y with this, get a new function, or whatever, and have a function and graph the function, or I just look at the graph itself and just move things around. That's it. So let's see here. This function here, notice that 8 is on the exact same level right there. And we see that the parent function is y equals absolute value of x. And of course, opens upward, and the origin, the origin is the vertex here, and the slope is 1 effectively. So all this says is either I can replace right there I just replace the x minus 4. Why? Because I shift right 4. So if I just replace it, there I go. I get that x minus 4 inside. Or the other thing is just to take each point and add a 4 to the x. Add 4 there, here, add 4 there, and that's it. So either replace point by point and just shift the points over, shift the important points and then draw, or essentially replace the x with x minus 4 with the function and then graph this function. So what about this one down here? What do the two graphs look like? So based on this parent function right here, based on this parent function here, what's the basic shape? And how does this one shift? Notice we're not comparing this to the parent function. We're comparing this to this whole function. But this parent function will tell you the basic shape. But tell me what happens to this function right there. So chat real quick with your neighbor. All right, this right here, the plus 4.2 is actually the opposite of what I see. So that means the negative means it's going to shift to the left. Left 4.2 relative to the x that's being cubed. Now, notice here, the difference from here to here is not negative 5. What is the change? Good. It goes down 6. Arithmetically, it goes down 6. And graphically, it also goes down 6. What about its shape? Both shapes.
Well, it makes like that little.
Both shapes make this little thingy here. Good. All right, so it's the exact same shape, but what's happening is that one of them is just shifting over. So it's just like we take that and just shift it left and then down 6, something like that. So next part here. So find the coordinates of a point. And the question, of course, we say is, what point? Well, any point. So I just pick a point that'll work in here and see where it goes over here. So for example, if I take y equals, and I plug in some number, 0, for example, so then that's going to give me a 1. So I start with the point 0, 1. And where does it map to? Where does it map to? Well, it's going to map to. So what we have to do is just apply what we did up here. We're going to subtract the 4.2. Subtract the 4.2 from here. So the new function is negative, or maps to 4.2, negative. And we have to go down 6 here. So from here, I subtract 6 to get negative 5. And talk about this one. What's the image of 0, 0 under the translation that maps the first to the second? Good, so we apply this translation effectively to here, so we subtract 4.2 there, and then we subtract 6 from the y to get this. And I do want to maybe make a clarification that this does not describe the translation, so maybe I should erase or delete the translation. What I'm just saying is that 0, 1 maps to here. This wasn't the translation. This is up here is the translation. So, all right, so if I were to write the translation down, it would say this: translation of my xy, so whatever the xy is, it maps to negative, so x minus 4.2 and y minus 6. So all we do is subtract 4.2 from the x and subtract 6 from the y to get from one point to the other, the pre-image to the image. Example 3, if the graph of y equals negative 1 over 2x squared is translated 8 units up and 17 units to the left, what's the equation for the image? So instead of up here, what I did was find the translation and apply it to each individual piece. So I just found a point and then mapped it, and then I found this point, used this point, and I mapped it over to here. This one is actually just trying to find the function. So what do we do? Well, units up means y minus 8 on the side of the y, and units to the left means x plus 17. So remember what our function says up at the very, very top. Notice what we replace them with. I just replaced the entire x with x minus h. I replace the entire y, doesn't matter where y is, on the left or the right side. Just wherever it is, I replace it with the minus the k. Now, since I'm going up, I'm going to say minus a positive. Since I'm going left, I'm going to minus a negative. There. So, okay. So all we do is replace it and then solve. So I'm going to take this and substitute it there. And I'm going to take this and substitute it inside the x. Inside the x with parentheses and all. So y minus 8 equals negative 1 over 2 times x plus 17 all squared. Now, I'm going to probably write this as a function in function form. So I'm going to get y by itself. So I'm just going to add the 8 to both sides. So my final result, written in function form, is this plus 17 quantity squared plus 8. And remember, this tells me about how things shift. Compared to the original one, I am moving left 17 here, and this one says up 8. And notice I put the plus k on the outside over here. Very poorly drawn here, but here's the parent function. Now, that's not this function here. This function I know is going to flip upside down and also get compressed a bit, but we haven't talked too much about that. So it's actually the blue, more like the blue here, but there is going to be some squashing that happens. Now, if I were to take this point right here and this point right here, what am I doing to those points? Well, I'm going to translate it up 8, so the whole thing's going to get shifted up 8, and to the left 17. So this guy is going to be way over here, and this guy's going to be way over here on the in the first quadrant, first and the second quadrant, actually mostly in the third quadrant there. All right, so the question here, if the graph is translated, what is the equation? So this is the answer. This is just giving you a graphical analysis, which was not part of the question. Just wanted to unpack it a little bit further. So as we look at this, we want to do a quick sketch. So the first thing we ask ourselves is, what does the parent function look like? Or what is the parent function? Both part of it. So here, the parent function is y equals 1 over x cubed, like so. And this is going to graph something like this, where it's kind of tight like that and pulls down like that. And the same thing, almost looks like a reflection. Actually is a reflection going that way. All right, so it's probably wise to start with that, because what we're going to do is move exactly that a certain amount. Good. So this one here means left 1, and this part here means up 4. Try that again. Down 4. Wait a tick. When is it up? When is it down? If this were on the other side with the y, and this is with the x, when it's with the y, it's the opposite. When it's with the x, it's the opposite. This one here, we isolated the y, so we moved it over. So it's exactly the same. So this is the same, and this one is the opposite here. So I have to resketch exactly this function right here, but I'm going to move everything left 1 and down 4. So Let's do that. Left 1 and down 4, which puts me here. This point goes left 1, down 1, 2, 3, and 4. So it puts me now here. My graph is off, so I will need to extend it out a little bit. And this one goes left 1 and down 4 to be put here. So I'm going to take exactly this graph now and now try to fit it in. So it goes like that and here. And this one is more like that and there. Left 1, down 4, left 1, down 4, and then we just regraph exactly as we see there. All right, as we look at this one, so you've all check your work against mine here. Shh. The first thing we want to see is what's the parent function. And clearly we see that the parent function is radical x. So let me change that. Y is equal to radical x. We know that its basic shape looks something like this. One thing that we want to pay attention to is when we do a sketch doesn't mean every single point is 100% accurate, but it does mean some things are accurate. So when you make your sketch, make sure to have the initial and one or two of these points spot on, okay, in the sketch, because the rest of it can just be an estimate. Second, before I even draw my crosshairs, which we have a tendency just to draw the origin, I want to see where I'm going first. So number 2 is what's my transformation, and clearly I am going to go right 3 and down 5. So if I did a quick sketch here and saw that, I'm going to go right 3 and down 5. So I need a lot of space down here. So let me just make sure to leave myself room down there. Make sure that when I do my sketch, the square root of 0 is 0. The square root of 4 is 2. So if I were to do my sketch, and the square root of 1 is 1, so it's got to do this, something like that. And then it keeps going like this, okay? And try to keep it as nice and curved as possible. Try to avoid like that. So all I have to do is shift the whole thing down. In fact, I'm going to shift those 3 points. Shift those 3 points down and right. 1, 2, 3, 1, 2, 3, and 4. So that puts me, 5 puts me there. This one is up there, and this one is right there. And there we go. And like I said earlier, when I made my sketch, I should have noted that quadrants 2 and 3 are not used at all. So I probably should have taken this whole thing and shifted it over that way.